Welcome to our electrical research channel. Uh, if you wish to get the models and publication support or collaborations work, please join to our WhatsApp group. The WhatsApp group link is available in description link. So today topic is the microgrid or standalone system, which consists of wind, PV, and a battery. Basically, in this model, I am going to explain like AC microgrids, and on your wish or your requirement, you can convert this model easily to the DC microgrid also, because all renewable energy sources are connected to the common DC link, so which can give the DC microgrid things. And from the common DC link, I used one inverter to operate the AC loads. So uh, actually, one PV module or one PV array I considered in this system. The PV array, which consists of uh, many number of modules. It is in your choice that you can select any number of modules, but the voltage rating should be the matching to the our system. And one wind turbine along with the PMSG, I mean permanent magnet synchronous generator based electrical power generation. These two I connected to the common DC link, uh, and I will explain each sources and each objectives. And before going to the this model explanation of this model, please subscribe our channel. Let's first I will start the model because it will take some time to complete the running process. So before explanation, I started this model. See, now it is running fine. And see, two renewable energy sources are there, but according to your wish, you can connect many number of renewable energy sources, or even you can connect multiple PV systems or multiple wind systems to common DC link. Here you can see that this is the rate parameters of the PV system which I modeled in MATLAB. Here 22 number of cells are connected in series to establish 666 volts. If you require some more voltage, you can increase the number of cells modules in connected in series, or if you require more power rating, you can make it in parallel connection of this complete arrays. Here the power is each module power is 7.10 into 30.3. I mean nearly 215 watts. Each module of PV capacity is 215 watts, and 22 are connected nearly 4.73 kilowatt is my capacity of the PV, and wind capacity is nearly 6.5 kilowatt. And see, I didn't use any MPPT converter, but I used P and O algorithm, which I explained in my previous videos. For complete analysis of this P and O, I mean watch my previous videos, and the complete modeling of the PV also I explained. And basically this is I done in 2013 version, so the same MATLAB model you can run in 2013 version. If you want to rebuild the same in 2013, you have to do some modifications, because whenever I bring the library functions, I done some modifications according to my model. So you you don't think that same blocks you can bring into your library and you can rebuild this model, or if you want to run this in higher versions, one thing you have to do that upgrade the model. And second one, some blocks will not be available in the same location of the your library, which I taken in from my library. So in that case, you have to replace the same blocks from your library, and you have to do some modifications, because already I taken some library functions and I did some modifications according to my operating conditions. Those also I will explain in details. What things we have to do the modifications, and what I done modifications, and everything I will explain you. And this is the basically battery. I connected the DC link voltage through bidirectional DC-DC converter, and for this bidirectional DC-DC converter, one switch is used to for the charging. I mean current can flow in this direction. This arrow is there, so in this direction current can flow and it can be charged. While discharging, it will act as a boost converter from the switch, and current will pass through these diodes. That is the reason we are using one more diode and anti-parallel with this switch, but there is no required of diode anti-parallel in this switch. So this switch will be act as a boost converter, and this switch will be act as a buck converter. Because my DC link voltage is nearly 660 and I selected nearly 300 volts of my battery. If same ratings, then more current cannot be dumped into the battery, so the always the DC link voltage should be more than and nearly double to the your battery ratings. I typed it 200, but it is actual ratings are these things 365 rated, and my initial charging is I taken as a nearly 80, but I didn't consider any SOC type controllers. See, two switches are there, and I taken the battery current, and based on battery current and based on reference battery current I can operate these two switches, whether it have to be charging mode or whether it have to be discharging mode. The same battery I connected to the DC link, the positive terminal, negative terminal. I taken the midpoint neutral because the phase voltages, my intention is to regulate the phase voltage instead of the line voltages. I want to regulate the phase voltages, because our distribution system, maximum our distribution system is single phase loads. So to maintain the power quality or to maintain the constant voltage species, I mean a common coupling point, we have to take care about the phase voltages instead of the line voltages, because all drops are not all phase drops are not equal in LC filter, across LC filter. It depends on the how much current is flowing through each fader or each phases. So the mainly wind turbine I model, like I taken the wind turbine model from the library, and I done the some modification that I, instead of you can open your model, and here you may get -1 as a constant gain, but I taken as a +1 because again I want to connect the 2 mass drive. So after 2 mass drive I connected the negative block before giving to the this PMSG. I connected the negative gain here. So these two blocks are available in your library. In 2013 also it is available, in the higher version also it is available, but I done the modification. So if you are directly bring your block, then you have to make it -1 in inside. I mean already -1 will be there, so in outside you have to multiply with again -1, because 2 mass model will take the only positive torque reference, and after the 2 mass model you have to make the negative gain to the to torque of the PMSG, because positive torque it will act as a motor and negative torque it will act as a generator, and there is no significance of pitch angle here. This is the normal rating, maximum rating of wind turbine, not equal to the generation. It is more than the generation because losses will be there. So 8.5 kilowatt, the same ratings I used here, 8.5 kilowatt and 8 point. These all parameters are you can manage it according to your wish. And after PMSG I connected one rectifier, diode rectifier, and I converted to the DC, and after that I used one MPPT controller with boost converter, and a controller depends on your torque. So I taken the speed and I calculated the reference torque by using this simple equation. Even I didn't consider some losses that J d omega by dt plus B omega, those losses I didn't consider, and I make it the simple controller. This is CP value, simple torque reference. I got it the torque reference with according to my maximum power. From torque reference and the voltage and speed I can get it the current, because torque into speed will be the power by voltage will give the reference current. So power I got it from torque and speed, and I divided by VD. VD means voltage across diode rectifier, and this is my reference current and this is the actual current. I am comparing with current controller, hysteresis loop. Then the pulses will go to here. So always this will work as a MPPT controller of the wind turbine. And the rated power, I told you that it is corresponding to the 10 meter per second. So whenever you are giving the more speed, then more power will be generated. So I calculated the power of the wind turbine, and I calculated the power of this PV, and I used VMPP, but afterwards I will tell you how we can use. and this is a simple battery controller with my reference is 660. In case of if you are not using any MPPT, I mean MPPT means it will regulate the PV voltage, output of PV voltage. So but here I directly connected the PV voltage to DC link. So this DC link voltage I can regulate it by the bidirectional DC-DC converter of the battery. So the bidirectional DC-DC converter of the battery can work as a MPPT of the PV system. You no need to connect any other MPPT circuits which can give the more cost of the system. So the thing is, if you require any MPP, I mean if you want to connect any MPPT converter separately, then you can manage it. But in that case, you should not select 22 cells because 22 will give the exactly 666 volts. So in that case, this V reference signal from P and O algorithm will be the reference voltage signal of your bidirectional DC-DC converter of the battery. So your PV voltage can be regulated at your V reference. Then it will work as a MPPT converter of exactly to the PV system. But the simple model I am explaining. So see, the simple thing is, if your DC link voltage, your DC voltage is more than your reference, I mean let us assume your reference is 660 and you are having more than 660, maybe 670, that means more DC power is available than the load. So more power is available means some power I have to dump into the battery. So the battery have to be charged. So see, simple thing is, if your DC link voltage is more than your reference, I mean negative will come here. Like the DC link voltage may be 670, so negative will come. Then negative output of PI. Negative current means charging, because I measure the current in this direction. This is the positive and this is the negative. This current will get into the charging of the battery. So negative reference. So battery current will go to the negative. So negative means 0 pulses will come. Whenever it is 0, through NOT gate, it can get the charging. I mean it will give the 1. So S2 should be your charging switch. S2 means here S2 pulse, not exactly switch. So the S2 pulse have to go to your charging mode. So this pulse I have to give to the charging of the switch. It will work as a buck converter, 600 to 300 or 660 to 300. It will go to the buck and battery can be quickly charging. Similarly, in reverse direction, I mean reverse operation, it can go for discharging mode. So my intention is I have to maintain my voltage 660 in all the conditions. And I connected 3 different kind of loads. Initially small load is there, 500 watts. It is very less. So small current will flow into the load. So it will give the poor quality of the voltages. Because the filter won't work for very small currents. If current is 0, then there is no use of the filter, L filter. After that, at around 0.5 seconds, I connected nearly 5 kilowatts. So my generation is more because my 2 generations will be more than the load. So battery will get the charging. So after 1 second, I connected 7 kilowatt. So in that case, my generation will be somewhat more because 500 plus 5 kilowatt means 5.5 plus nearly 7. So 12.5 kilowatt. So it will be more power is required. So battery have to be discharged. Let's see how it is working. So this is the basically I am measuring the load power and wind generation, PV generation and battery power. So you can see this is the very initial condition where 500 watts only connected. See, this is my PV and this is my wind. So the total of this is my generation and this is the load. So rest of power is going to my battery. So nearly 10 kilowatt is dumping into the battery. Once 5 kilowatt is connected the load, I mean the first load is connected 5 kilowatts at around 0.5 seconds. You can see at 0.5 seconds 5 kilowatt load is I connected 4 kilowatt of load. So in that case, battery taking power is I mean reducing the charging power of the battery, because the still generation is more than the load. So after 1 second again I connected a 7 kilowatt. So in that case my generation is very less. I mean the total generation is very less compared to the load, and battery is now get to discharging. Negative power of the battery is giving the charging, and positive power of the battery is representing the discharging mode. To make this, I am connected one inverter controller, but before going to the inverter controller I have to maintain the battery DC link voltage. I mean the DC link voltage of the system should be the constant. See, always my system DC link voltage is nearly 660. So 660, this is the discharging mode, this is the charging mode. Discharging, charging, discharging, charging, it will operate like this. And this is the very transient period, and which is also very limited mode. I mean only, like you can see, only 5 volts drop or 6 volts drop, it is less than 1% of the DC link voltage. And once the DC link voltage is fixed, then I can easily regulate my inverter voltage. See, from inverter I am measuring both phase voltages and line voltages. From phase voltages I considered again RMS, and RMS I consider into the, by per unit of RMS I consider into the 1 of per unit. Per unit I taken 1 by 231. So my RMS voltage should be stable at 231 volts. And after 231 it will give the per unit. So this is the per unit of my present RMS voltage of the PCC, and I am comparing to the one. After that, this I am giving to the PI controller. This is actual 3 PIs because I am using the bus system. So the PI will give the modulation index of each phase, and from modulation index of each phase I am multiplying with simple unit sine waves. Unit sine waves are required because the frequency have to be maintained and sinusoidal PWM have to be produced to generate the pulses. So the once I multiplied this unit sine wave with my modulation index, it will give the V modulation index into sine omega t. So according to that modulation index, I can regulate the RMS voltage, I mean magnitude of voltage, and frequency of sine wave can be regulated the frequency of output voltage of the inverter. So once I got the reference sine wave, I am giving simple PWM generator. This is also I bring it from the library, but I done some modifications. I removed these blocks instead inside, but you no need to do any modifications. You can directly bring your system, and you have to take that. You have to remove this tick, that internal generation modulation. If you are clicking the international modulation index, I mean internal generation modulation index, it will ask the parameters, and once you clicked that, it will be connected to the system. So maybe some students may I mean by default or maybe by mistake they will click on this thing. So if you are click on this, you cannot you are unable to maintain regulate your DC, I mean AC RMS according to your load. If load is more, then AC RMS will be reduced because the modulation index is fixing. But to avoid that conditions, simply I remove this. Once my output is not coming, simply I can say that this is by accidentally someone clicked on this button. So for that I removed this, but if you wish, then you can maintain it. It is not an issue. It is your I mean your logic and your things. So the power I explained, and the MPPT also you can see that this the MPPT is regulating fine. The MPPT is working very fine. The torque and reference torque both are matching, and you can see my RMS voltage and all these things. See, this the first one is the modulation index. Always I am maintaining the modulation index based on my load. The modulation index is changing. If more load, then more modulation index is required to maintain that this RMS voltage of AC, I mean at PCC, because more load, more drop will be there, more modulation index can increase your inverter voltages. So after the drop, PCC can get the regulated RMS voltage. This is my phase RMS voltage. You can see always I am getting 231. So this is one load in connected at one. See, before one and after one also I got the 231 volts because my reference is 231 RMS. This is my instantaneous sine waves. You can see the line voltages of sine waves, uh, before this it is very I mean very fluctuating things because uh, only 500 watts of load is connected. It is very nominal load, and this you can see the my currents. I mean the load current. See, very small currents at before 0.5 seconds because of 500 volts. After that, the currents are like this. Even you can connect the unbalanced load also. This will work fine, very fine. So this is very simple model for understanding purpose, and this is the basic thing. According to your requirement, you can change any parameters or anything. It can work for any value, even for megawatts also it can work. But whenever you want to do the megawatt systems or more than kilowatts or gigawatts or whatever maybe, multiple PVs or multiple events, you have to manage the all capacitance values and resistance and inductance, everything. I mean the parameters of these things are required, and DC link voltage is also required. I hope you understand this thing, and please forward this video to many, I mean, who are required in your circle, and please join in our WhatsApp group so that you can get this kind of models. I with free of cost. I mean, you no need to pay any cost, and collaboration work also you can do for quality of research publications and all these things. Thank you very much.